This is a section which will be expanded on in the next chapter. We're going to introduce a couple pieces here and then add in one more piece next chapter. First, 3 quick review items to lay the groundwork for the one theorem this time. So far we have covered a lot of linear measurements in this class. We have simply had line segments. We have had perimeters of polygons which had a linear measurement. We've had a radius of a circle or the height of a trapezoid. Heck, even though it is curved, the circumference of a circle is also a linear measurement, since it shows how long the line segment would be if you could unroll and flatten out a circle. All of those are linear measurements, and we've had so much more. No matter which one we are talking about, though, every linear measurement is measured in units, not units squared. All of this should be review. This should also be review, but every area measurement is measured in units squared. You may think it is weird that I would say every area measurement, as we have really only done one up to now. But in the next chapter, there will be various types of area we talk about. Base area, lateral area, surface area, and more. Sound fun? No matter which area we are talking about, they are always measured in units squared. One last piece of review. Some chapters ago, we dealt with similar figures. Congruent figures are still similar, but most of the time our similar figures were different sizes. The theorem that we are working with in this section only works with similar figures, so you need to remember how they work. One of the most important things to remember for this lesson is that a pair of similar figures has a scale factor between them, which tells you the relative sizes of the two shapes. We will be using the scale factor today. This is the one theorem from this section. If you have two similar figures, then they have a scale factor. The ratio of any corresponding linear measurement is a to b. So all of those linear measurements I reviewed a minute ago apply. The corresponding heights, or radii, or perimeters, or some other linear measurement are all in the same ratio as the scale factor. This is the first part of the theorem. The second part says that any corresponding area measurement is in the ratio of a squared to b squared. Remember, this only works with similar figures. Here's how many students like to remember it. If the pieces you are comparing are measured in units, then use a to b. If the pieces you are measuring are measured in units squared, then use a squared to b squared. Make sense? Here's a quick example. Let's say I have two similar pentagons that have areas of 1,075 centimeters squared and 2,107 centimeters squared. If the perimeter of the smaller pentagon is 175 centimeters, then what is the perimeter of the larger pentagon? There are two ratios that are always central to these types of problems. They came from the last theorem. It is usually a good idea to figure out which one of those you were given and then solve for the other one. The two ratios are going to be used for almost every single one of these types of problems. Lots of students find filling out a chart like this helpful. Let's now look at the problem. We were given two areas and one perimeter. We should probably start with the value we have for both shapes, which is the area. You should know that the areas are in the ratio of a squared to b squared. Thus, we know that a squared over b squared will be 1,075 centimeters squared over 2,107 centimeters squared. But don't put that into the chart. If you want to make your life significantly easier, you should always, is that enough always? Reduce first. Let your calculator do the work and reduce that fraction for you. If you plug that somewhat ugly fraction into your calculator and reduce, you'll get a much more manageable number. They are also perfect squares. Suppose that is a coincidence? Now we can fill that number into our chart. Now we can fill out that last block in our chart. If a squared to b squared is 25 to 49, we need to take square roots to get down to a to b. The square root of 25 is 5, and the square root of 49 is 7, so I can put 5 to 7 in our chart now. If you hadn't reduced first, you would be dealing with the square root of 1,075 and the square root of 2,107. Sound fun? I'm guessing the square root of 25 and 49 are probably much more to your liking. Always reduce first. Now that the chart is filled in, now what do? Reading our problem, our final goal was to find a perimeter. And which of those two ratios in our chart will perimeter use? The top one, a to b. So to solve this problem, we need to use 5 to 7. What goes in the other side, though? Well, we know the smaller pentagon has a length of 175 centimeters. Should that go on top or on the bottom of our fraction? That number is for the smaller pentagon, so it should go with the smaller number, the 5. So it goes on top. And we put an x on the bottom since that is the number we need to find. Then we simply cross multiply, and after the algebra is done, we have the perimeter of the larger pentagon is 245 centimeters. Just remember to always reduce first, and always find both a to b and a squared to b squared. Those are the keys to all of these problems.